Hello. Hello. Good morning, everyone. Welcome back to the Earth Engine India community webinar series. This is the um, eighth one in our series. We have a guest speaker today, as well as our community old timer Craig D'Souza. The guest speaker this time will be Abhishek Potnis. We have a lot of interesting stuff lined up. As usual, remember to share your questions on the YouTube live chat. The slides are, I'm going to post the slides there right now. You can follow along, but you can also share all your questions on the chat, and we will get to the questions at the end of the webinar today. So let's get right down to it. Like I said, the guest speaker we have today is Abhishek Potnis. He's in IIT Bombay. He's been doing a lot of research using geospatial data and satellite imagery on disaster mapping, disaster detection and mapping, and so on. Today he'll talk about some of the work he's done in the flood detection and mapping area. Yeah. So Abhishek, can you take over?
Thank you, Pradeep. So I'll share my screen for the presentation. Is everyone able to see my screen?
Yes, Abhishek. The slides are visible. Thanks.
Okay, great. Thank you. So good morning, everyone. I'm Abhishek Potnis. I'm a PhD student at the Center of Studies in Resources Engineering at IIT Bombay. I'll be talking about flood mapping with Google Earth Engine. So, floods are among the Earth's most common and most destructive natural disasters. Thousands are rendered homeless, while numerous succumb to this dreadful calamity during floods. Moreover, urban floods is a particularly serious issue that has resulted in catastrophic loss of life and property in recent years. Uh, Specifically, in Mumbai, we had a case of severe flooding this week from July 2nd. IMD reported about 375 millimeter of rainfall was received in just a span of 24 hours. That caused lots of waterlogging on streets. Some electrocution cases were also reported, and about 22 fatalities were reported. So, disasters such as floods not only ruin our habitat but also adversely affect the nation's economy at large. There is a dire need actually for effective disaster management and assessment techniques to help alleviate the losses caused by such disasters. So one of the solutions that one of the possible solutions to alleviate these losses comes from the technologies developed in the domain of remote sensing. So typically, remote sensing platforms categorized for disaster assessment are classified into two types: the spaceborne platforms and the airborne platforms. So the spaceborne platforms have on board remote sensing sensors and that are mounted. So spaceborne platforms include satellites, whereas airborne platforms include airplanes that are mounted with cameras, hyperspectral cameras, and of course the popular nowadays the drones. So these type of remote sensing platforms form an apt choice during a disaster assessment and management scenario, typically when the area on the ground is inaccessible. So in case of flooding, one cannot actually go there for surveying and assessing how much loss has been caused and where are the damages due to the floods. So remote sensing platforms form an apt choice for such kind of cases. So with that in mind, I'd like to talk about the satellite products that can be used for disaster assessment. So out of the many satellites that have been launched from different places on in the world, the Landsat and the Sentinel are the two popular satellite programs that have been initiated. So the Landsat program, initiated by the United States Space Agency, that is NASA, has a series of satellites that they have launched typically for Earth observations. The latest one being Landsat 8, that was launched in the February of 2013. So the Landsat 8 is known to have a spatial resolution of about 30 meters. So one pixel of in the imagery of the satellite captured by Landsat maps to 30 meters on the Earth's surface. Similarly, Sentinel is another satellite program that was initiated under the Copernicus program by European Space Agency. So even Sentinel has a series of satellites that have been launched. So the Sentinel 2A has a spatial resolution of 10 meters, while the Sentinel 1 has a spatial resolution that is down to about 5 meters. So again, these satellites that have been launched have a different type of remote sensing sensors on board them. So just to give you a brief, remote sensing is classified into two types, that is active remote sensing and passive remote sensing. So active remote sensing involves some kind of radiation that is emitted by the satellite, that is emitted by the sensors, that hits the surface of the Earth, and the reflected radiation is then captured by these sensors, and the analysis is further done. Whereas passive remote sensing involves measuring the radiation that is emitted from the Earth's surface. So there is no form of radiation that is emitted by the sensors in passive remote sensing. So typically, for instance, the mobile cameras that we use, right? So they can be seen as an example of passive remote sensing, because they simply capture the wavelengths that are reflected back into the camera. They do not emit any radiation as such. Coming back to a disaster scenario, specifically speaking about the flood domain. So during the flood, typically what happens is there are overcast conditions, including cloud cover. Dense clouds can be seen. So if seen from a satellite's perspective, so the active remote sensing platforms that capture imagery in the visible domain, that is the RGB and probably like infrared. So these platforms are not very effective, because these sensors, to be precise, these sensors are not very effective because all they can see are the clouds from the satellite's perspective. So typically, for disasters such as floods, uh, the active remote sensing option is encouraged. So in case of active remote sensing, microwave remote sensing, to be precise, is used. So microwave remote sensing platforms or microwave remote sensing sensors emit microwave radiation. So that has a shorter wavelength and has a capacity to penetrate through the clouds and reach the Earth's surface. So, and also one important thing is, in case of active remote sensing, at night time it is difficult to infer what we are actually seeing on the ground. But that is not the case with active remote sensing. And active remote sensing, again, because of the advantage of microwave remote sensing that uses shortwave radiation, so short wavelength radiation. So the satellite sensors are typically termed as all day and all weather satellite sensors. So Sentinel 1, the satellite has a C-band synthetic aperture radar, so C-band SAR that we call it. So in short, so that is one of the sensors that is typically encouraged to use in case of disaster scenarios such as flood. So I have put together a couple of case studies for this particular talk. Uh, and I'll be discussing on those. So both these case studies are for different regions of the world, and in both the scripts that I've put together use the Sentinel One C-band synthetic aperture radar imagery. So I'll quickly move on to the case studies. So the first case study that we'll discuss is of the Hurricane Harvey that hit in uh, August 2017 in the United States of America. So uh, the now typically because we are talking about flooding, The chain of events is that what happened was the Hurricane Harvey caused flooding in some parts of the United States. So I am going to focus on the flooding that happened because of this hurricane. Floods in general are classified into like three or four subtypes. One is the flash floods, and other is the fluvial or the riverine flooding that is called. So the flash floods are typical floods that are caused by extreme events such as rainfall, like high amounts of precipitation that happens over a region, and the runoff water is not absorbed into the ground. So that results in waterlogging on the streets and ultimately causing flooding and great damage to property and life. So that is about the flash floods. And the riverine flood or the fluvial flood, as the name suggests, is because of a river or a water body overflowing. So the banks of the river overflow and the water gets inundated about along the edges of the water body, causing the areas near the rivers to be flooded. So, in particularly in this case, the Hurricane Harvey, this Colorado River in Texas, USA, uh, uh, was known to be the result of fluvial flooding. So, in this script that I have put together here, you can see the RGB satellite imagery captured by the Sentinel-2 multispectral sensor on board the Sentinel-2. So, as I said, it is the imagery is captured in the visible range. So the red, green, blue channels have been visualized in this screen that we see. So, and the C-band synthetic aperture radar from Sentinel-1 has been used to detect flooding in this particular case study. So, essentially, what the script does is that it takes two imageries, one of the post Hurricane Harvey and one of the pre Hurricane Harvey, C-band SAR imagery, and computes the basic operation of difference. So, post Hurricane Harvey image minus the pre Hurricane Harvey image, followed by a smoothing operation to minimize the speckle noise that we have, and followed by thresholding to identify the flooded regions. So we can see actually which parts of the satellite imagery were actually flooded. So uh, so this is the result of the difference operation followed by the smoothing and thresholding. So we can clearly see that the brown regions indicate how the flooding has actually happened when we did the difference operation on Google Earth Engine. So this is again a very basic operation that Google Earth Engine, like there are a host of operations that Google Earth Engine has to offer, but these were the two scripts that I experimented with when I first learned about Google Earth Engine, just to get an insight of how the flooding actually happens, and I found it pretty useful. Like we can actually see how the flooding has happened on the coastal regions of the river Colorado. So we can clearly conclude from this result that most of the flooding that happened because of Hurricane Harvey was fluvial flooding, that is riverine flooding. And accordingly, since now we know that the flooding typically during the hurricanes happens because of the river overflowing, so measures like evacuation or other water conservation measures can be taken to alleviate the losses caused by such kinds of flooding. So this was the Hurricane Harvey case study that I had considered using basic operations in Google Earth Engine. Uh, Similarly, this is the second case study of the Flinders River in Australia, in Queensland to be precise. So, this is a more recent case study. So, in January 2019, we can see that the Flinders River is actually this one, and the other rivers that you can see are the tributaries of this river. So, this was in January 2019, and what happened was in February of 2019, due to excessive amounts of rainfall, the river actually swelled to this particular size. So the brown regions that you see are the swollen version of the Flinders River. So the width of the river is has been reported to be around about 60 kilometers in width. So this was again caused by excessive rainfall. So again, the difference operation of the C-band SAR imagery was performed, followed by a smoothing and thresholding to identify this. So again, we can conclude that this kind of flooding is a case of riverine flooding or fluvial flooding. Uh, so yeah, so the idea was, to understand how and where actually the inundation patterns happen when the flood occurs. So these were the two case studies that I had taken up, the Hurricane Harvey and the Flinders River was one. Now, for these two case studies, the satellite products that were used were the Sentinel-1 C-band SAR and the Sentinel-2 MSI multispectral imagery. So both of these satellite products are openly available on the Google Earth Engine in data catalog. So one can easily just import it into the platform and perform analysis and perform the processing and analysis and derive actionable insights from the analysis. So, but then the beauty of Google Earth Engine platform is that it is not restricted to you only using the satellite products that are by default into the platform that can be imported, but it also supports uploading custom raster satellite imagery. So uh, for this particular like the feature of Google Earth Engine, I have put together a small this screenshot, this GIF for understanding. So this is more related to my PhD thesis topic on urban floods. So I focus my research area on the urban floods, typically focusing on the streets in cities, how the land use land cover classes interact with one another spatially during a flood scenario. So this particular satellite imagery is not available in Google Earth Engine. It is of a different satellite, a Worldview 2 satellite, and it is a very high resolution satellite imagery. Uh, so I think the spatial resolution is about 0.43 meters, and so so the idea of adding this in my talk was to demonstrate that we can upload a custom satellite imagery onto Google Earth Engine and perform analysis. So as I mentioned that I primarily work on classifying a satellite imagery into different LULC classes. Like the machine should be able to predict that this particular pixel belongs to this particular class. So for that, machine learning techniques or approaches are preferred. So again, in machine learning, supervised and unsupervised classification approaches can be taken. So in this particular case, I have taken the supervised machine learning approach, and so you can see these polygons that have been drawn in the GIF. Yeah, so it will just come up. So yeah, so these green, red, blue, and yellow polygons that I have manually annotated using Google Earth Engine's editing tools. So that was my way of telling the machine that these are the classes. So the blue polygons indicate water, the flood water. The red polygons indicate buildings. The green polygons indicate vegetation, and the yellow polygons indicate fallow land. So these were the classes that I specifically told the machine. In the machine learning terms, this was the training data that I provided to the machine learning algorithm. And Google Earth Engine again has a host of inbuilt machine learning algorithms into it. So the most simplest to use among them is the random forest, which just takes as input the satellite imagery, the training data in terms of geometries, and one hyperparameter, that is the number of trees. So I guess for a number of trees of 50, yeah, so the result of the random forest will just come up. Yeah. So this was the result of the random forest classifier. So you can see that the entire image is filled up, and so each pixel is now assigned a class. So even those pixels that were not trained by me initially have been assigned the class mostly correctly of the flood water, the buildings, the vegetation, and the fallow land. So so the conclusion of this particular slide, is to demonstrate the Earth Engine's capability to work with custom uploaded satellite imagery. Of course, the satellite imagery needs to be georeferenced before uploading, and then you can perform your processing and analysis over such satellite imagery. So uh, yeah, so I would like to conclude my talk here. So to summarize my talk, we started with discussing the seriousness of the disaster of floods, the dire need of effective disaster assessment and management techniques that can help alleviate losses caused by the flood disaster. Remote sensing forms an apt solution in case of situations when the area on the ground is not accessible, and particularly microwave remote sensing from synthetic aperture radar is a good choice during the flood scenario when there is significant cloud cover and there is a necessity of being able to see satellite imageries during night too. So we discussed two case studies of the Hurricane Harvey and the Flinders River, and concluded that both the floodings were the cases of riverine flooding or fluvial flooding caused by the overflowing of the river Colorado in case of Hurricane Harvey, and the Flinders River in Australia. And lastly, we elaborated on the feature of Google Earth Engine to work with customly uploaded raster data and do classification over it. So yeah, with that, I would like to conclude this talk. Thank you. I sincerely thank the Earth Engine community to give me this opportunity to discuss my work with you all. Thank you. Thank you, Pradeep. So I'll stop my screen share. Yeah, I think I have stopped my sharing of the screen. Yeah.
Yeah, great. Thanks. Thank you so much, Abhishek. That was great. With this being monsoon season, and we've already seen in the news many instances of flash floods and cities getting inundated and daily lives getting disrupted very badly, and many people suffering a lot. This topic is definitely highly relevant and important, and some good solutions are really needed. So thanks for sharing your work on this. This also reminds me of how this topic brings together some topics we've dealt with in earlier webinars also. So those of you in the audience, if you missed those webinars, you should just definitely go check them out. There was one on disasters, landslides in particular, by Raj Bhagat a few webinars ago. There was also flood mapping, change in water extents in lakes and rivers due to drought, all of that kind of disaster monitoring stuff. And in our share a skills part, we had a segment on SAR imagery just a couple of webinars ago. That was all basic fundamentals about SAR imagery, but this is a very nice example of how some of that can be used in a very practical scenario. So this is a nice extension to come into as well. So yeah, thanks for bringing up this topic, and it was a great talk. It also brings together some of the things we also talked about earlier. So that's very nice as well. So anyway, so let's moving on with today's fair. Next, we'll have Craig Dsouza. He'll help us understand how to deal with clouds in satellite imagery. Craig?
Hey Pradeep. Yeah, so going ahead with the topic that I had in mind for teacher skill this time was just trying to see if we can do something really simple within cloud masking, but not the entirety of cloud masking, because there are different approaches to doing that. But what I wanted to see is if we can just take a look at Bitmask, because Bitmasks are something that you find that many sources of satellite imagery have bitmasks in their documentation, and someone who's not too familiar with the concept of bitmasks or binary images may find it a little difficult to uh, understand something like that and get started. So that's what I'm going to cover today. I'll just quickly switch to sharing my slides. Yeah, so this is a good initial image just to get started with. Most of the I mean, the bitmasks that I'll be covering in today's examples are more than just 8. What you see here is an 8-bit bit mask. So by 8-bit, I just mean that there are 8 ones or zeros in order. And so in some of the imagery, you may find 12-bit, you may find 16-bit, but in each of the cases, the concept is pretty similar. What you have to do is take a look at to convert to understand what the bitmask is saying in terms of in binary terms. You need to essentially take a decimal value, which when you use your inspector tool to query an image in Earth Engine, you'll essentially get a decimal value. So that can be the thing that is initially confusing. So, for example, I have here, I'm looking at a modus image, and within that modus image, you're looking at a state QA band. So so state QA. Let's move to the documentation for a second. Um, So state QA, you can have a look here, and in the documentation, it shows that it's a 16-bit bit mask. So all the way from zero based indexing all the way up to 15. But when you query an Earth Engine image, you see with state QA, you see a number like 8397, and that is in fact a decimal number. It's not a binary. It's not directly shown here as a bit mask with the number of ones and zeros. What you can easily do there to interpret that is take your calculator that each of you have in your PCs, and go switch to maybe programmer mode, and type in your number. So here it says 8397. So that's the decimal number as 8397. But you can also see the binary representation down here below. So that is a 16, it shows you a 16-bit binary number. So now we'll get into how do we interpret that binary number. So I'll start quickly just with an example from with Landsat actually. So say so within this Landsat imagery you have um, 11 bits, right? So and when I said earlier that there are generally 12 or 16 bits, there may be only fewer than 12 or 16 bits that contain the information that is important, um, but anything after the 10th bit here would essentially be can essentially be filled with zeros, but the bit mask information would be stored as a total of 12 or 16 bits. So in this case, say we want to, what we want to really find out is um, where is the presence of clouds or cloud shadows. So Landsat surface reflectance imagery, that's the documentation that we're looking at here, um, has already been provided with along with this pixel QA band, and that band has been generated after running the CF mask algorithm, which is a cloud masking algorithm, and you you essentially get this pixel QA band as a result of that, and within that band, if we want to mask out clouds, if we want to use that band to mask out clouds or cloud shadows in our resulting Landsat imagery, what we need is essentially only the 5th bit and the 3rd bit. So essentially, what we need to do is a 3-step process. So I'll move to the code here. So this code, there are examples to the example scripts which show you how to run this code in the docs, in the slides that have been shared with you. Um, so essentially, we're declaring a function, and within that function, we're declaring two masks. So the first mask is just um, this one and a double less than sign and a three. So this notation may be a little unfamiliar to some people in case you've not worked with it before. But this is called a bitwise left shift operator. So essentially, what you're telling this, what you're declaring this variable as, is initially declaring it as a one, but then you're saying left shift that one by three spaces. So once you take, once you do that, what you get is the cloud shadow bitmask with in this form. So the one you can see here has been left shifted by three spaces. So it was originally in the units sort of place, but then it's been moved three spaces to the left. So that will essentially help you get your cloud shadow information. Similarly, the cloud bitmask has a one, but it's shifted five spaces to the left. This is again because um, your cloud information is in bit 5, your cloud shadow information is in bit 3. Um, so then what we do is evaluate it using a longer conditional operation, wherein you just take the QA band, which may be a completely long, is a 12-bit, 16-bit band, and you're extracting just the two individual pieces of information that you want. So, and you're making it a binary band. So what I've said here is declare a variable called cloud yes no. So that is essentially taking the QA band and using a bitwise and over the cloud shadow bitmask, and then using that same uh, bitwise and over the clouds bitmask. So only if both the cloud shadow is one and the cloud bitmask is one, um, sorry, is zero, not one. So if only if both the cloud shadow bitmask bit of information is zero and the cloud bit of information is zero, will it declare it as a um, valid pixel essentially. And then the not equal to here is just to reverse it. So reversing the one to a zero. Um, then essentially you return that image with these two bands. So that I'll take a look at what that looks like here. Give it a second to load. Yeah, but you can see here that this is a Landsat collection that's mosaic, and you're looking at the true color visualization initially. And on top of that, you're looking at the cloud yes or no band that was generated using the 2-bit mask. So essentially, wherever it is a clear pixel, you'll have a zero, and wherever it is a cloudy pixel, you'll have a one. So that's what you get after um, after running this little script here. Now, similarly, if I wanted to do the same thing for a Modus composite, so Modus has these 8-day composites that are published, and within that, it has within that imagery, it has a band called state QA. So within state QA, there are additional bits of information. It's not just cloud related, cloud or cloud shadow related information. There's also land water. There's also if I switch quickly here, there's also land water. There's also aerosols as the type of cloud and some other stuff, but we're only going to essentially take a look at clouds in this example here. Um, but what I'm telling you can equally be applied to look at the other bits of information other than the cloud bits. So here for the modus imagery, for the cloud bits, we're essentially looking at 0, 1, and 2. Um, so in this case, I'll switch to the code. Um, this is just a slightly different approach to generating the bitmask, but essentially, what you have to keep in mind is that what you want at the end is something like this that's shown here at the bottom. Um, because and so this is 1 1 right at the end. So why do you want this 1 1 right at the end? That's because your state QA band has the cloud information in bits 0 and 1. Um, and this is unlike the Landsat imagery, which had your cloud information in a single bit, which was bit 5. Here in the modus imagery, it is in two consecutive bits, 0 and 1. So essentially, what we're going for is generating a bit mask which is 0 everywhere except for the last two bits, which are both ones. So essentially, you declare what that boundary is that you want um, bits from 0 to 1. So you declare cloud QA start and end, and then your initial bit mask is 0, and then you run a for loop which gets you from QA start to QA end. And this is just a simple operation where if I say, I'll show you one initial example. So if you say 2 to the 0th power, that's essentially 1. So bitmask in the first instance of the loop goes from the initial value of 0 plus 1. So in the next iteration of the loop, your bitmask is already 1, and then you're adding to that 2 to the first power. So that's 2, and again that's 2 as a binary number. So essentially, what you're doing is, sorry, that up. So this allows you to sort of declare any number of bits that you want um, in your calculator. So you can essentially, in the first instance, you're taking 2 to the first power, um, and then in the next instance you're taking, sorry, switch back to this. 2 to the first power, so that gives you 3. So 3 in binary you'll see is 0011, which is your bit mask that you're going for. You just have to imagine a certain number of zeros to the left of that up to 16 bits. So that's another approach to get the bit mask, but the concept is pretty similar. And then everything after that is also again similar, that you take uh, your bit mask, and in this case, because your bit mask is two bits rather than one bit, you have done the operation slightly differently, because what you see here is that only 0 and 3 are clear. 1 and 2 is cloudy or mixed. So essentially, I've done a bitwise XOR, exclusive OR, with the band and with the number 2. So what is the number 2 as binary? That is essentially 0010. So that basically is saying that um, only isolate pixels that are not cloudy. So we're only eliminating 1 here out of the entire combination. If it is a mixed pixel, if it's not set, if it is clear, we're preserving those pixels with the bitwise XOR band. And then not equal to is again to reverse it. And then what you get here at the end is, show you that result quickly. This is the true color visualization. And the cloud yes or no band on top of that. So everywhere where it is black is essentially uh, is essentially cloud free. So what you'll see is that the modus cloud mass is much more stringent than, no wait, did I say that right? Yeah. So it's the reverse. Everywhere where it's white is cloud free in this image. Yeah. So the modus cloud mass is much more stringent as compared to the Landsat one, but essentially you get the results that you want. So yeah, that was a little bit of a primer in using Bitmasks. I will come back to and stop sharing. So if there are any questions, feel free to post it to the YouTube chat, and I'll be happy to take them. Thank you.
Thanks, Craig. Yeah, that's a very crucial little skill to have when we are dealing with optical imagery, satellite imagery, and all of that. So, thank you so much for putting together that little segment. Definitely useful to know, and it's an innocuous topic. I think even I had since I've worked a little bit on these data sets, now I'm a little bit familiar with this. So it was a nice jogging of my memory as well. But I do remember that in the early days, it took a little bit of careful thinking and understanding to figure out exactly how this works. So yeah, thanks a lot for putting together that little segment. So we can come to the questions now, because we are both our speakers have finished making their presentations. So let's just go over and check if there are any questions from the audience. Um, there are a few questions. So, for example, there are two for Abhishek and two for Craig. I don't know. We can go in whichever order. Abhishek, do you want to take the
Yeah,
questions that come to you? Okay,
yeah.
great. Go ahead.
So yeah, both the questions are particularly on the synthetic aperture radar imagery. I'll try my best to answer these questions. I primarily work with visible satellite imagery from UAVs, drones, and very high resolution satellite imagery. So I am not a microwave remote sensing expert per se. So Pradeep, Craig, please feel free to correct me or add to like what I have to answer. Yeah. Uh, so uh, so the first question is, how do you select polarization in the SAR imagery for flood mapping? So I would like to start with a bit of background. So I did mention in my talk that SAR, synthetic aperture radar, falls in the active remote sensing classification, wherein the radiation is emitted from the satellite sensor and then again received from what is backscattered. So the polarizations are actually, there are different kinds of polarizations like HH, which stands for horizontal horizontal, or VV, which stands for vertical horizontal, or VH, and so on. So these polarizations actually indicate the polarization in which you are transmitting and the polarization in which you are receiving. So, for instance, the HH polarization will indicate, the transmission is happening in using the horizontal polarization, and the reception is also like happening in the horizontal polarization. Similarly, VH and VV. So typically, these polarizations are selected on the area of interest that we are looking for in a satellite imagery. For example, during a flood scenario, the primary thing that we are looking for is flood water, like the water that is waterlogged on the on the Earth's surface. So in these scenarios, literature suggests that it is best to offer VV or HS polarization. But having said that, it is always better to using Google Earth Engine, we can visualize these polarizations as imageries, and it is better to plot a histogram and see how the histogram is spread, and whether different classes are captured accordingly. And yeah, so typically I would say HH or VV polarization is a good choice for an flood scenario. But yeah, it is always better to plot the histogram and see for yourself whichever works best for your particular data set. So yeah, so that would be the answer to my first question. And the second question states that it would be useful if you show some type of smoothing applied to your Sentinel-1 imagery before comparison and your experience. So yeah, so in the two case studies that I've taken up of Hurricane Harvey and the Flinders River one. So I have used the basic filtering operation of focal median that the Google Earth Engine has to offer. So it is a morphological reducer that filters the imagery to alleviate the speckle noise. I have looked into there is this leaf filter that is known to produce better results, but apparently leaf filter for this particular data set only produce slightly sharper inundations of the flood pattern. So again, leaf filter is not readily available in Google Earth Engine. So yeah, so I think I did see an implementation that is out there for leaf filter in Google Earth Engine. Yeah, so that's about it, Pradeep.
Yeah, thanks. That's interesting. So the question about the polarization was from me. I was curious. I wanted to know. So yeah, thanks. That's useful to know. I'll definitely check it out more. And the person from the audience who asked the other question, yeah, if there are any follow-ups, those are also still welcome. Please ask. We are still looking out for any questions you might have. But
Also, Pradeep, sorry
yes,
to
please,
interrupt. Yeah,
please.
in the slides, I have added the Google Earth Engine code scripts too for these two particular case studies. And in the code, actually, I have added some references. So those of you who are interested to dive deep into the filters and the morphological operations, there is a blog URL that I found interesting. So I have added the blog URL in the references section of the Google Earth Engine code script. So yeah, maybe you can look into that. Sorry to interrupt again, Pradeep. Back
No,
to you.
no,
Yeah.
no, not at all. Yeah, thanks for adding that as well. So those are definitely useful resources. We'll for those of you who may not be familiar, so the slide deck that we've shared already on the chat window, that will remain as a resource that will go along with this webinar. So once this webinar gets published on our YouTube channel, the link to the slide deck will also go along there, and all these resources will be accessible through there. So um, just so you know where to look for them when you come back to them. Anyway, so moving on. So the other question was for Craig.
Yeah,
Craig, you want to take that?
I can take that. Yeah. So the question is essentially, I'll read it out. Could you tell us how this QA band approach is different from cloud underscore cover, which is often an image metadata property in Landsat images? So essentially, um, cloud underscore cover, the metadata property is essentially a single property which is ranges from 0 to 100. So essentially it's a percentage of your tile image that has clouds in it. So it's a slightly more coarse approach to removing clouds. It could work in a situation where your imagery is mostly cloud free. You just want to remove the few images which are of lower quality meaning say 20% cloud cover, and you have enough other images that are completely cloud free, so you can use those to compute your composite or mosaic. But often it is the case that most of our images, say especially if you're looking at the monsoon season in India, it is the case that most of your images would have cloud cover in it to a great degree. So if you only use the metadata property cloud cover to filter out images which are, say, less than 20, I mean not less than, greater than 20% cloud cover, then you're essentially eliminating all your images. So instead of doing that, using the QA band is an alternate approach where you're not evaluating the full image at a time. You're not, which is what cloud cover is doing, the metadata property. You're evaluating a single pixel at a time. So the QA band has a different value for every single pixel of your Landsat image. So you can therefore say that, okay, if this pixel is cloud free, let's retain it. Whereas when you're using the cloud cover property, you're essentially saying this this tiled image has too many clouds in it, so remove the entire image. So you're throwing away many pixels which are also probably valid and cloud free along with that. So I hope that explains things well enough.
Yeah, I think so. Thanks for that. Yeah, so basically, cloud cover is an image level property. So when you're filtering by at the image level, you'd use that. But when you're filtering every pixel, you use the QA bands, which is a pixel level property. Great. Okay. Excellent. So those are the questions we had for today. So all the resources, like I said, are available in the slide deck. If any one of you interested can go back to it at any point and refer back to anything from today. But I see that there are no more questions on the live chat. So I guess we'll call it a day for today then. Thanks to all of you for joining in, and I hope you will find the material the speakers presented today useful. Please refer back to the published video at any point in time, go back to the slides and any of the resources linked in there. We hope that all of that will come in useful to you at any point. Remember to check us out on the community website as well as join us on the Google group, the link for which is available through the website. And thanks for joining us today, and we'll see you again next time. Bye.